Let's go ahead and get started. I don't think I have any administrative announcements, aside from that the second problem set is here for you to pick up, and also posted on the course website. Hopefully the first problem set wasn't particularly difficult. Wasn't particularly easy, presumably, but hopefully it wasn't too bad. They'll be getting slightly more difficult, but I don't think substantially more difficult. Did you guys find the first problem set impossible, totally impossible? No. Okay. Except for the pencil problem, which is sort of like one of these famous problems that you have to think everyone should think about and chew on and test themselves against. It's a great little problem, but that one is sort of tricky. But hopefully everything else was reasonably straightforward. Okay, my goal today is to continue our discussion of time evolution in quantum mechanics. So today, my goal really is to continue our attempt to understand physically what the wave function of a quantum mechanical system represents, at least in terms of our classical intuition. And this will lead us, within the next 20 minutes or so, to what I consider one of the most profound reformulations of our understanding of quantum mechanics, namely the path integral formulation of quantum mechanics, which is the topic that will occupy us for the rest of this week and probably at least a little bit into next week. Okay. So good stuff coming up today. Buckle your seatbelts. So, let me just remind you of the Schrodinger equation. So this is the time-dependent Schrodinger equation for a particle. So for a particle moving in one dimension, of course, we would have the one-dimensional derivative here, psi, the second derivative of psi with respect to x. And for a particle moving in 3 dimensions, we would have the square, the Laplacian of psi. Or if a particle moving in 10 dimensions, we would have the 10-dimensional Laplacian, or something like that. Okay. And last time, I concluded by trying to understand a little bit the physical interpretation of the wave function psi based on the properties of this time-dependent Schrodinger equation. So, for example, I noted that if one defines the probability density, which is the norm squared of psi, so this is the probability of finding the particle at a given point x as a function of time, then it obeys a continuity equation where rho dot plus the gradient of a current j is equal to 0, where j was, I remind you from last time, IH bar over 2m psi star grad psi minus grad psi star psi, or stated a little bit more simply, this is of course just equal to h bar over m times the imaginary part of psi star times the gradient of psi. So this continuity equation, I remind you, was just a simple consequence of taking the expression for the probability density and plugging it into the time-dependent Schrodinger equation and using that to derive an expression for rho dot and noticing that rho dot was the gradient of something, and then comparing this to our intuition from continuum mechanics or fluid mechanics, we identified the thing that it was a gradient of as the probability current. Okay. So if rho is the probability density, namely the likelihood that you would find a particle at a given position as a function of time, then J is the probability current. And so what this means is that although quantum mechanics is confusing, it still bears a great deal of similarities with theories of physics that we know and love, so that, for example, the probability of observing the particle at a given point in time obeys a local conservation law, i.e. a continuity equation, just like any other continuum mechanics system, so that, for example, the change in the probability of observing the particle at a given time is proportional to the flux of probability out of that point as a function of time. That's the physical content of the continuity equation. Now, in fact, we can take this set of considerations a great deal further in trying to understand the physical description of the quantum mechanical wave function. So I remind you that the wave function psi is a complex quantity. The norm of psi is given by the probability density. But in addition to the norm, it has a phase, which I will call S over h bar. And one of the things which will be instructive for us to do will be to work out the form of Schrodinger's equation in terms of these variables rho and s. Was there a question? I saw some confused looks. Yeah. That's the square root. Is that helpful? Okay, good. Yes, that's a square root. Right. So all I've done here is write the complex number psi in the usual r e to the I theta polar form, the norm and the argument. The norm is what we call the probability density, or rather the square root of the probability density. And the phase is something that I'm calling S. Okay? And I'm including a factor of h bar with malice of forethought. So let's work out the Schrodinger equation. I h bar psi dot is minus h bar squared over 2m times the Laplacian of psi plus v psi in terms of rho and s. Well, actually, even before I do that, let me just make one comment, which is that this probability current can also be written as rho over m times the gradient of s. In order to see that, just take this form for the wave function that I have written here and plug it in to the definition of J. And you will see, what does the gradient do? Well, that brings down a factor, here, let's work that out a little bit more explicitly. So, psi star gradient of psi, using this above expression, is, well, from the psi star, we have the square root of rho times e to the minus is over h bar. And the gradient of psi, well, what is that? That's the sum of two terms. One term which comes from the gradient of rho. So let's just, I won't even bother writing that out. Well, okay, I'll write it out. It's rho to the minus 1/2 times the gradient of rho just using the chain rule for differentiation. And then we have plus I over h bar times the gradient of s, all times e to the I, s over h bar. The phases cancel, and when we take the imaginary part, we throw away this piece, and we're just left with the gradient of s, and we see that the imaginary part of this is just going to be, let's see if I get all of the factors right, 1 over h bar. Sorry, there was a factor of rho out, square root of rho out front, times rho times the gradient of s. Okay. So you can see that another expression for the probability current is that it's rho times the gradient of the phase of the wave function. So this phase of the wave function is obviously an important quantity. And the question that I would like to ask is, what physically does this phase S represent? So in particular, what I would like to understand is, what does this phase S represent in the semiclassical limit where h bar goes to 0? Of course, quantum mechanics is very confusing, but in the limit where h bar goes to 0, quantum mechanics should go over to classical mechanics. I understand what the interpretation of rho is in that limit. It's the probability of finding a particle somewhere. So what is the interpretation of S? Okay. So in order to understand that, I would just like to take this expression for psi written in polar coordinates and plug it into the time-dependent Schrodinger equation. So let's go ahead and do that. So the left-hand side of the time-dependent Schrodinger equation is I h bar times the time derivative of psi, which written in terms of the this expression for psi, written in terms of the square root of rho and a phase, is just the time derivative of the square root of rho plus I over h bar times the square root of rho times the time derivative of s, all times that phase e to the I s h over h bar. And that phase will also appear on the right-hand side of the equation. So I'll just cancel it out on both sides. And then the right-hand side of this equation is minus h bar squared over 2m times the second derivative of psi. And the second derivative of psi is going to be the sum of 4 terms. So there'll be one term where the derivative hits the square root of rho twice. There'll be one term where the derivative hits the square root of rho once, and where and once hits the s up in the exponential. There'll be another term where the derivative will hit the s up in the exponential twice. And then there'll be a fourth term where the derivative first hits s to bring down a gradient of s, and then it hits that gradient again to give you grad squared s. And then, of course, there'll be the potential term, the square root of rho times b. So this is just a Schrodinger equation written in polar coordinates. Now, what I'd like to do is investigate the limit where h bar goes to 0. When h bar goes to 0, most of these terms become irrelevant. The limit when h bar goes to 0 gets rid of all of the terms on the right-hand side, except for this term, the square root of rho times s dot. So what do we have? We have minus s dot times the square root of rho. Now, there's going to be a factor of the square root of rho on the right-hand side of the equation, so I'll just factor it out and not write it in this equation. And then on the right-hand side of the equation, the only term that survives from the gradient is this term. This is 1 over 2m times the gradient of s squared plus v. Or, if I want to rewrite this, I could write this as s dot plus 1 over 2m times the gradient of s squared plus v is equal to 0. The interesting thing about this equation, yes, question?
Yeah, sorry, I'm not sure I understand why letting h bar to 0 goes to the classical limit.
Let's put it this way. The only reason that classical physics is different from quantum physics, let's put it this way. H bar is very small. Okay. From the point of our classical perspective, the reason why we can ignore quantum effects most of the time is that h bar is a very small number. If I wanted to try and estimate the size of quantum effects in some physical system, what I would do is, one way of doing that is I could calculate, things like the typical position and momentum of the parts of the system, take their product that has the same dimension as h bar, and if it's very large compared to h bar, then I can ignore quantum effects. So the extent to which classical mechanics is valid is the extent to which h bar is small relative to what other scales you have in your problem that have the same dimensions as h bar. That's just dimensional analysis. And so if I take h bar to be very, very small, then that's saying that I'm considering the system in the limit where classical mechanics should be valid. Okay. Is that clear? Okay, good. So the h bar going to 0 limit is just a fancy way of saying I'm considering the classical limit of a quantum mechanical system. Okay. As we've learned, the formulation of quantum mechanics is fundamentally different from that of classical mechanics. And so a very interesting and important thing to try and do is understand how quantum mechanics will go over to classical mechanics in the limit where it should. Okay. And a concise way of saying that is in the limit where h bar is going to be 0. Now, h bar is a dimensionful quantity, so it doesn't make sense to say h bar going to 0 on its own. You should really say h bar going to 0 compared to something else which has the same dimensions. So implicitly, h bar has dimensions, for example, of energy times time. So if you're studying, say, a pencil balanced on its tip falling over, then you should calculate the typical energy and the typical time scale, compare that to h bar to determine whether or not quantum mechanics is relevant for that problem. And indeed, it's whether quantum mechanics is relevant is a statement that the ratio energy times time over h bar is going to be big or small. And h bar being very small is the same as saying that classical physics should be valid. But that's a sort of a crucial point, so I'm glad you asked. Is that clear to everyone why h bar going to 0 is the classical limit? Good. So let's stare at that equation in the box. The first thing that we notice about this equation is that it has no h bars in it. And we obtained it in a classical limit. So that means that that means that everything appearing in this equation should have a classical interpretation. V has a perfectly good classical interpretation. It's the potential that our particle moves in. So what is the classical interpretation of S? Well, let me ask anyone if they recognize this equation. Okay. Let me, in fact, tell you the name of this equation, and then ask you again if you recognize it. Okay. Not quite. This is called the Hamilton-Jacobi equation. This is the lecture where we test how good your classical mechanics course was. See, when I was teaching classical mechanics, you learned all about the Hamilton-Jacobi equation. What is the Hamilton-Jacobi equation? It is the equation of motion obeyed by the action S. And I remind you that the action S is usually regarded as a functional of the possible path that a system can take through configuration space. Or, said a little more prosaically, in the case of a particle, it would be the path that the particle can take through space. And there's a special set of paths, namely those which are the classical paths that the system does take. And if we take the action of the system and we view it as a function of the endpoints of a classical path, then it obeys a differential equation, and the differential equation it obeys is the one that I've drawn on a box up here. Okay. So just to reiterate that, usually you think of the action as a function of paths, okay? But you could also specify the endpoints of the path and find the classical trajectory that solves the equations of motion. And then you could view the action, I should put curly braces there instead of square braces, as a function of time and the initial and the final endpoint. And so if, for example, you fix the initial endpoint and view it as a function of the final endpoint and time, then you view S as a function of two variables, x final and time, and it obeys the Hamilton-Jacobi equation. So this gives us an interpretation for the phase of the wave function. The phase of the quantum mechanical wave function is when h bar goes to 0, the classical action. In the semiclassical limit, the interpretation of the norm of the wave function is as the probability density, and the phase of the wave function is just the classical action. I can't overemphasize how important this is. Okay. One of the things that is always slightly confusing to people about quantum mechanics, at least at first sight, is that it's really most naturally viewed as a quantum version of the Hamiltonian form of classical mechanics, not as a version of the Lagrangian form of classical mechanics. And this is the first time that we've seen a Lagrangian or an action appearing in quantum mechanics. And so this will lead us to a new formulation of the laws of quantum mechanics, which should be viewed as the quantum version of the Lagrangian formulation of classical physics, as opposed to the Hamiltonian formulation. And indeed, this observation is the starting point for the path integral formulation of quantum mechanics, which is what I'm going to start considering now. But before I do that, let me just see if there are any questions. Any questions? Yes?
You said just a minute ago in the semiclassical limit, the norm is seen as the what?
Well, it's the probability density. Okay. Now, for a classical particle that has a definite position, that norm is going to be a delta function. Okay. So for a classical particle with a definite position, you should really regard the wave function as being a delta function in the radial component and the classical action in its phase. Good. Any questions? Excellent. Okay. I'm very excited. This is my favorite part of this class. So, given this set of considerations, my goal is to find an alternate formulation, or in particular to find an alternate way of understanding time evolution in quantum mechanics, and in particular to understand an alternate way to compute the time evolution operator u of t and t prime, which I remind you is the quantity that plays the fundamental role in determining how the state of a quantum system changes in time. So, for the purpose of this lecture and next lecture, I would like to consider the case of just a particle moving in one dimension, although, of course, what I'm going to say can be generalized, in which case what I'm going to try and compute are the matrix elements of the time evolution operator in position space. So in position space, we would study the wave function of psi as a function of time. And this would be equal to, just by inserting a complete set of states, the matrix element of u times the wave function of the particle at some earlier time t prime. So it's the integral dx prime of the matrix element of u between x and x prime times the wave function at some earlier time. So sometimes when we have integrals of this sort, we call it a convolution. So it's a convolution of this matrix element of the unitary time evolution operator with the wave function at some earlier time. Or if we have not an integral but a sum, we call this matrix multiplication. That's another name for this expression. And my goal is to compute the matrix elements of this time evolution operator. And if you think about it, the matrix elements of this time evolution operator have a very simple interpretation. So the state x prime appearing here is simply the state where the particle is localized at a particular point in position space, and likewise for the state x. And so the matrix element of the time evolution operator is simply the amplitude, the quantum mechanical amplitude, for the particle which starts at a point x prime and t prime to end up at a point x at some later time t. Okay. And this is obviously a very important quantity, and in fact, it has a special name. It is called the propagator. So that xt, x prime t prime, is the amplitude for the particle to start at a position x prime at time t prime and end up at a position x at some later time t. And this propagator, of course, plays a very important role, because once you know the propagator, then you know the unitary time evolution operator, and you can figure out the time evolution of an arbitrary quantum state, okay, just by convolving this propagator with the wave function psi. So in physics, we often give a special name to those functions which you can use to solve the equations of motion by performing an integral of this sort. We call them Green's functions. And in particular, this is the Green's function for the time-dependent Schrodinger equation. Presumably, you've at least heard the word Green's function in the context of your electromagnetism class. Is that correct? Okay. If you haven't heard it, don't worry. It's just, at this point, a bit of jargon without any more physical content than what I have already said and written in this equation. But it's the sort of word that you might see later in your lives, as this is a. And the important point about this propagator, and the reason why it's called a Green's function, is that it is also a solution of Schrodinger's equation. Okay. It's just a special case of Schrodinger's equation where we happen to start the particle in a delta function in position space, rather than in some more generic initial state, psi, at some early time t prime. And so it solves Schrodinger's equation that I h bar d by dt of this propagator is equal to minus h bar squared over 2m times the second derivative plus v acting on this propagator. Sorry, I'm a little squashed in there. Hopefully you can read that. Is it clear that this solves the Schrodinger equation? Okay. All it is just a case of the wave. All the propagator is, if you regard it as a function of x and t, is it's the wave function if you happen to have started at a position space eigenstate at some earlier time t prime. Okay. So let's compute it. And I'd like to compute it by making the following sort of tricky observation. So let me note that this propagator has the following property. It's the amplitude for a particle to go from x prime at t prime to x at t. But I could rewrite that in a sort of slick way by considering some intermediate time t1 that lies between t and t prime. And I could write this as the amplitude for the particle to go first from x prime and t prime to x1 at some time t1, and then to go from x1 at time t1 to the final position x at time t. Okay. So I could imagine choosing some intermediate time t1 in between t and t prime, and the amplitude for the particle to go from x prime at t prime to x at t is just the sum over all possible intermediate points, x1, where the particle sits at time t1, and I calculate the amplitude to go from x prime t prime to x1 t1, and then x1 t1 to x prime t prime. And then I sum over all possible positions the particle could be at the this intermediate time. So this should be true for any t1. And in fact, this is just a consequence. And indeed, it's just a rewriting of the basic feature of unitary time evolution operators, namely that the unitary time evolution operator to go from t prime to t is the product of the operators u from t to t1 and u from t1 to t prime. So, when I introduced the fourth postulate of quantum mechanics, I made a big deal about this composition property of the unitary time evolution operator. And the reason why I made a big deal about it is that it is the basic property of quantum mechanics which allows you to derive a path integral formulation. Okay, I'm not done here. So rather than inserting one intermediate time t1, let's insert n of them. So I could also imagine inserting n intermediate times that I'll call dx1, that I'll call the intermediate times t1 up to tn minus 1, and the position of the particle at those times as x1 up to xn minus 1. And then, because of the composition property of the unitary time evolution operator, I can just rewrite this as a product of these propagators going between all of these intermediate points. So what did I call it? xn minus 1, tn minus 1, with x prime, t prime. So, what is the physical picture I want you to keep in mind? Well, we have this final time, t1, so let me draw a little picture of the path that this particle is taking, where the horizontal axis will be time, and the vertical axis will be position. So we have this final time, t, at which the particle is sitting at some time x, and we have some initial time t prime, at which the particle is sitting at some position x prime. And then I have imagined dividing up this time interval into a bunch of little pieces. So I've chosen a time t1, t2, and so forth, all the way up to tn minus 1. And the particle is at some positions at these intermediate times. And I'm going to choose my time interval delta t to be very small. So what is delta t? Delta t is the spacing between ti minus 1, which is t prime or t minus t prime divided by n, or I guess I call it little n here, which is the total number of intervals. And you can view this, so then this equation is the statement that the amplitude to go from the initial to the final time is simply the amplitude to go from here to here, so from here to here, then from here to here, and so on and so forth. And the point is that I'm integrating over all of these intermediate positions, x1, x2, and so forth. And so in the limit where n goes to infinity, which is to say that the time spacing between them goes to 0, this is a sum over all paths that the particle could take and the only condition is that the path starts at a position x prime at time t prime and ends at a position x at time t. Because when you integrate over x1, x2, and so forth, and then you take the limit where delta t is getting very small, essentially what you're doing is you're summing over all possible paths that you can take between these 2 points. So what that means is that we expect that there should be a formula for this propagator which can be written as an integral over all paths that the particle can take between these 2 points. So I'll use a special symbol capital D of x to denote the sum over all possible paths. And I've written x of t here just to indicate and remind ourselves that x is going to be a function of t. And the boundary conditions on this integral, so all integrals have to have boundary conditions in order for them to be given by actual numbers. And the boundary conditions are that the x at t prime is equal to x prime, and that x of t is equal to x. Okay. In order to keep the notation from getting too confusing, what I'll do is I'll rename this x final, t final, and x initial, and t initial, just so that I'm not using the symbol x in too many different ways. So x at t initial is x initial, and x at t final is x final. And it should be a path integral of something. So this is an integral over all paths. And then the question, the name of the game, is to identify the integrand. And, in fact, if you remember what we did not 20 minutes ago when we discovered the Hamilton-Jacobi equation, I gave you a very strong hint about what the integrand is, at least if you remember some basic features of integrals in the saddle point approximation. Before I describe that, however, let me pause and see if there are any questions. Yes?
This formulation doesn't work if V is time dependent, right? Because then your eigenstates change.
If what is time?
The potential.
Yeah.
Does it still work?
This will still work. Still work. Right now I'm considering the simple case where V is time independent, but if a Hamiltonian is time dependent, then there's a straightforward generalization of this, which will be clear, hopefully, when I complete this derivation. Good. Good question? Other questions? Okay. Now, in order to figure out what this something is, consider the semiclassical limit, where h bar goes to 0. In that case, there is a unique classical trajectory from x initial at time t initial to x final at time t final. That's just classical mechanics. And we know what the propagator should be in this limit. We know that the propagator should be given by the exponential of the classical action of this classical path divided by h bar. So S is the integral from t initial to t final dt of the Lagrangian regarded as evaluated on the solution to the classical equations of motion. So where S is evaluated on the classical equation of motion, and what is the definition of the classical equation of motion from the action point of view? So, i.e., S regarded as a function of the classical path is evaluated on the solution to the Euler-Lagrange equation, which says that the variation of S with respect to the classical path, i.e. dl by dx minus d by dt of dl by dx dot, is equal to 0. So the integrand is some sort of functional of the paths x of t such that when h bar goes to 0, the integral over all paths of that integrand is equal to e to the is over h bar evaluated at the place where the derivative of s with respect to the path, i.e. the variation of s with respect to the path, is equal to 0. Okay. That's a bit of a hint. And the hint will become more clear if I remind you of a particular method of approximating integrals known as the saddle point approximation. How many of you have seen the saddle point approximation? Okay. For some reason, it doesn't ever seem to be taught. So I will not remind you about it. I will tell you about it. It's also known as the stationary phase approximation in some contexts. Have you guys seen that? You still haven't seen it. Interesting. Okay. It's pretty easy. It makes perfect intuitive sense. So, before trying to understand saddle point approximations to infinite dimensional path integrals, consider the simpler case of a one-dimensional integral. Let's consider an integral. I'll give it a name. I'll call it z, which is an integral dx, where now x is just a one-dimensional variable, of some function e to the lambda f of x, where f of x is some function. So I'll just imagine that we plot f of x as a function of x. And, of course, in order for this integral to converge, when we integrate it from minus infinity to infinity, f is going to have to go to minus infinity as x goes to plus or minus infinity. And we wish to understand how to approximate this integral in the limit where lambda is very large. so as lambda is very large, this integral is dominated by the place where f of x has a maximum. Okay. Hopefully that should be clear. E to the lambda f of x is going to be very big when lambda is big at the place where f has a maximum. So in particular, it's dominated by the point where f prime of x is equal to 0, namely at the maximum. And in general, there could be other local maxima rather than global maxima, which will also give subleading contributions to this integral. And z is well approximated by the sum over these local maxima, which I'll denote x naught. So these are x naught such that f prime of x naught is equal to 0, of the value of the integral at that point. So this is hopefully reasonably clear. Is that reasonably clear? All I'm saying is that a good approximation to an integral is to find the places where the integrand is maximized. That's it. That's all this says. Okay. And to compute the value of the integrand at the place where it's maximized. And then, by taking lambda to be very large, I'm looking at the approximation where it's really only these local maxima that are giving the dominant contribution. Let me, just one sec. And then there are going to be corrections to this formula. So for example, there's one correction which you're going to compute on one of your next problem sets. So the leading correction is determined by the properties of the function near the saddle point. Okay. In particular, it's given by the second derivative of f at the saddle point. And then there are going to be further subleading corrections that will be determined in terms of all the higher derivatives. In principle, if you computed this infinite series of subleading corrections, you would then obtain an exact expression for this integral. Okay, there were a couple of questions. Yes?
Well, my first thought is that f prime of x naught is also going to 0 at the local minimum.
Yes. Those will give, so indeed, one also has to be careful about that. They will indeed also contribute, but because they're local minimums, the contributions will be smaller. They'll be subdominant. So we really only care about this thing we really only care in the large lambda limit about the global maximum of the function. Okay. I'm including a sum over all points where f prime is equal to 0, because in some cases formally, when you're considering path integrals, you would want to consider such things. But in all of the cases, but whenever you do, you need to take into account the fact that it's highly subleading. Okay. In the context of quantum mechanics, we often are able to give a physical interpretation to those subleading saddles as well. Okay. Just as a point of terminology, each x naught is called a saddle. Why is it called a saddle? Well, it's just a place where f has a local maximum or minimum. Okay. And this approximation says that the integral is approximately a sum over saddle points. Another question. Yes.
So suppose we have a second function, f hat of x, whereas that f was just sort of squished by a factor of 2.
Yes.
That sum would stay the same, wouldn't it?
Yes.
But the integral would be
indeed.
Maybe half as big.
Yeah. Well, you can see that in the leading piece, the e to lambda f of x naught, you wouldn't see that effect in the leading saddle point approximation. You would see it in f double prime. Indeed, if you squash the function by a factor of 2, f double prime will change by a factor of 2. Okay. So that's where it would come in. Like I said, in the large lambda limit, this is just an approximation to the function. And it's an approximation where, at least if you ignore all of the ... terms, you're throwing away a lot of information about the function. Good question. Other questions? Okay. So let's remind, so what does this say? This says that the integral of a function which is e to the lambda something is very well approximated by e to the lambda something, evaluated at the place where the derivative of something is equal to 0. Yes?
Do you know 1 plus 2 plus...
No, actually. No? Yes. You're going to, don't worry, you're going to derive that formula. Okay. If you're bored during this class, check this formula for a Gaussian integral. Okay. Indeed, that square root of 2 pi, that's the integral of e to the minus x squared. Okay. And so this comes by Taylor expanding f near the maximum. Okay, so you imagine Taylor expanding f near its local maximum. And then the 0th order in the Taylor expansion gives you 0. The first order is 0 because f prime is equal to 0 at that point. So the first correction is the integral is the second term, x minus x naught squared times f double prime in the saddle point approximation. That's a Gaussian integral. You know how to do Gaussian integrals. It'll be the square root of 2 pi over f double prime. Okay, I did the problem. I did it for you then. Okay, but you'll do it again on your problems then. Good. Any other questions? Excuse me. Well, this then tells us the answer to our question. This tells us that if we take as our formula for the propagator in the path integral language, that the propagator is the sum over all paths times the exponential of I times the classical action divided by h bar, then as h bar goes to 0, we just use the saddle point approximation, where lambda is 1 over h bar, to find that the propagator will then approach e to the is over h bar, where s is evaluated at the point where its derivative with respect to the path is equal to 0, i.e. at the classical path. We could call it x classical as a function of t, which solves the Euler-Lagrange equation, namely, which solves the classical equation of motion. Is that clear? So we know that based on the general composition property of unitary time evolution operators, that the propagator must be a path integral. And by looking at the semiclassical limit, we have been able to make an educated guess for what the integrand of that path integral should be. So my goal is now to prove that this is indeed the correct expression for the propagator, and I will do that by checking that this solves the equations of motion. And in particular, that this solves the Schrodinger equation. Namely, that IH bar times d by dt of this propagator for fixed x initial and time initial is a solution of the time-dependent Schrodinger equation. So you might need to roll up your sleeves, because this is one of those hairy little calculations which you need to think about a little carefully, and you might need to go through it again in the privacy of your own homes. So before I do this calculation, let me just make sure that that we're all on the same page and they understand exactly what's going on here. Okay. Good. So how do we compute the integral dx, the sum over all paths of e to the if over h bar? Okay. So first of all, we need to ask how, in principle, we would like to define this path integral. So before trying to define this path integral, an infinite dimensional integral where I integrate over all paths, let's recall the definition of a one-dimensional integral. So how do you define a one-dimensional integral? So the way that you define a one-dimensional integral is you imagine approximating the integral dx by a sum over some finite number of points times delta x. Or to be a little more specific, let's imagine that you have some function, okay? So this is some function f of x as a function of x. So what you do is you imagine approximating that function at a series of points, x1, x2, and so forth. So x1, x2, all the way up to xn. And then you evaluate the function on those set of points, and the integral dx of f of x is the sum over n of f evaluated at those points times the distance delta x between those points. So here delta x would be the range of integration, in this case xn minus x1 over n. And then this approximation will become exact in the limit where n goes to infinity. Okay. So the way that you define an integral is you break it up into some discrete sum, and then you take the limit where all of these delta x's become very small. So just as in this case, we approximated a function by its values on some set of points. For a path integral, let us approximate its values. In particular, let us approximate the functional that appears in the integrand by its values on some discrete set of paths. So, for example, we could let us imagine that we have, say, some t initial here, and the particle starts at some point x initial. Let us, as we did earlier, imagine calculating the amplitude from t initial at x initial at t initial to x final at t final by defining a bunch of intermediate times. I'll call them t1 up to tn minus 1. And rather than trying to define the full path integral, let us imagine the approximation where we just have a particle that moves on this sort of discrete path given by a sum of line segments that are all connected at points x1, x2, and so forth. And then the time separation, delta t, is given by t final minus t initial over the total number of segments. And we will, at the end of the day, take the limit where delta t is going to 0, i.e. where n, the number of segments, is going to infinity. And in order to make my notation a little bit more concise, I'll call x initial x0 and x final xn, just to make this a little bit more, the notation to be a little bit more concise. So that the propagator is then going to be given by the limit where n goes to infinity of the integral over x1 all the way up to xn minus 1 of the exponential of I over h bar of the classical action evaluated on this funny-looking discrete path. And just as in the classical case, I remind you there was this normalization factor delta x, which we had to put in order to keep the limit finite as n goes to infinity. There's going to be some normalization factor here that I'll call capital N. And indeed, we expect that there'll be one normalization factor for each one of the intervals. So I expect that there should be some normalization factor to the nth power. And I'm going to determine this normalization factor by demanding that this guy solves the Schrodinger equation with the usual normalization of the states, namely that all of the states remain unit normalized. Okay. So that normalization factor is fixed by the statement that the time evolution operator is unitary, or that probability is conserved, or that all of the states will remain unit normalized. Okay, is that clear? Everyone with me so far? Good. Okay. Let's go ahead and compute this guy. So what is S on this funny-looking path where I've discretized my path and written it as the joining of a bunch of straight line segments? So S is the integral dt over the whole path of the Lagrangian. And I can break that integral into a bunch of sums. So I'll think about the sum from t initial, from ti to ti plus 1, and then sum I going from 0, I suppose it would be to n minus 1, of the Lagrangian. And we're considering simple particle mechanics in one dimension, where the Lagrangian is 1/2 m x dot squared minus v. So in the limit where n is very large, namely where the delta t is becoming very small, I can approximate the integral dt of the Lagrangian as follows. I can approximate it by delta t times 1/2 m times the difference xi minus xi plus 1 over 2. So that's just the square of over delta t. That's just the square of the velocity minus v evaluated at xi. Okay. So all I've done here is I've imagined that delta t is very small, and then 1/2 m times the velocity squared is just 1/2 m times the difference between, say, x1 and x0. For example, if you wanted to calculate the velocity along that straight line segment. And then I've added in the potential v at the point xi. Now, if you wanted to try and make this a little more accurate, you could take the potential at the point halfway between xi plus 1 and xi plus 2 or something like that. At the end of the day, we're taking the limit where delta t is very small, and so that these points are very close to each other, so that's not going to matter. Everyone with me so far? Questions? So that means that this path integral is given by the limit where n goes to infinity of this normalization factor times the product, I goes from 0 to n minus 1, of the integral dxi times the exponential of I over h bar times this this approximated action, which was m over 2 delta t times xi minus xi plus 1 squared minus delta t times v. So what I've done here is I've taken e to the is over h, and because s is a sum, you can write that as a product of exponentials, and I've written one exponential here, and I'm taking the product over all I. And this is supposed to be equal to the propagator x of t to x prime of t prime to x of t. So in order to determine whether this solves Schrodinger's equation, let us imagine varying the endpoint. We want to understand whether this obeys some differential equation as a function of x and t. So let's imagine infinitesimally varying the endpoint, the end time t of this expression, in order to determine the derivative of this expression with respect to t. So instead, let's compute the amplitude to go from x prime at t to x at t plus delta t, rather than x at t. And by comparing this to the expression at x of t, I'll be able to determine the derivative of this propagator with respect to time and see whether it's equal to the Hamiltonian times the propagator. So what happens when I add one more time? So what happens when I vary this time? Well, so I've chosen this time interval delta t to agree with the time interval that I chose above, so that this new propagator is just given by inserting one more additional time interval. So that this is going to be equal to n times the integral dxn of e of the exponential of I over h bar m over 2 delta t xn. So let's say it would be x minus xn squared minus delta t times v times the original propagator, now going from x prime and t prime to xn at time tn. So all I've done here is I've rewritten this expression up here with a slightly different endpoint, and notice that because I've added one more time interval, I need to add one more integral over some intermediate position, which would be xn. And this should be equal to, in the limit where delta t is very small, 1 plus delta t times d by dt of the propagator x of t to x prime at t prime. And so what I would now like to do is, so I've expanded the left-hand side to first order in delta t. So let's expand the right-hand side to first order in delta t. So let me just rewrite this slightly. So this will be n times the integral dxn of e to the I m. Here, let me just give myself a little more room. So this is n times the integral dxn times e to the I m x minus xn squared over 2 h bar delta t times, let's expand that e to the I over h bar delta tv to first order in delta t. So that's 1 minus I over h bar delta t times v plus terms that are higher order in delta t that aren't going to matter. And then let's imagine Taylor expanding this guy. So we want to understand a differential equation that's obeyed by the propagator as a function x and t. Whereas on the right-hand side of this equation, we have a propagator at xn and tn. But xn and tn are going to be very close to x and t because delta t is very small. So I can then Taylor expand this. So this will be xt, x prime, t prime, plus the first order term in that expansion, which will be linear in x minus xn. But then I would have the integral of an odd function of x minus xn from minus infinity to infinity, and that's going to vanish. So the first non-zero term of this Taylor expansion will be 1/2 x minus xn squared times the derivative dx squared of this propagator xt, x prime, t prime, plus dot, dot, dot. Okay. Everyone with me so far? Yes. This is the Taylor expansion for this term right here. So I want to understand the differential equation obeyed by that guy. And so I need to compare it to this guy. And so I need to expand in the Taylor expansion where xn is viewed as being very close to x. So I'm expanding in derivatives with respect to x of that propagator. Yes. And tn, of course, is another name for t. Remember our notation. Good. Okay. Now we're done. All we need to do is do some integrals. So the integral of, so one of the integrals we need to do is of this phase, integral dxn, e to the I m, x minus xn, squared over 2 h bar delta t. So what is that integral? Well, that's just some straightforward Gaussian integral, which is easy to do. It's the square root of 2 pi I h bar delta t divided by m. Right? Just by dimensional analysis, you can see that if you rescale x by a factor of this square root of h bar delta t over m, you need this integrand to have it's going to be an overall factor of the square root of h bar delta t over m. Okay? That's just dimensional analysis. And then you just do the Gaussian integral to get all the factors of 2 pi correct. And likewise, we have to do the integral of this term here. So we have to do the integral dxn of this phase, e to the I m, x minus xn squared over 2 h bar delta t times x minus xn squared. And this is going to be that same factor, 2 pi I h bar delta t divided by m times something else, which you know has to be linear in h bar delta t over m, again by dimensional analysis. And if you do the integral, it's easy to do. You just get I h bar delta t divided by m. Okay, so let's start using this to compare the left-hand and the right-hand side of this equation. So the first thing that you notice is that this 1 here has to be equal to n times that 1 times that expression. So that means that in order to get the 1's to agree, we need to fix this normalization constant to be the square root of m divided by 2 pi I h bar delta t. So that's just to get the ones to agree. That's just comparing the normalization of the wave function on the two different sides of this equation. So we should consider that just as part of the definition of the path integral. So now let's look at the terms in this equation that are linear in delta t. So on the right-hand side of that equation, let's just go ahead and rewrite this term up here. The term linear in delta t was delta t times d by dt of this propagator. And the terms on the right-hand side, which are going to be linear in delta t, well, you're going to have this term here. So there's that normalization constant n, which will cancel the factor coming from this integrand here, times minus I over h bar, delta t times v, times the propagator. Right? Okay. That's this term here. And then there'll be the term coming from here, where we have to use this integral. So that is going to be, again, this factor over here that's canceled by this normalization factor. So there should be a plus I h bar delta t over m, that's this factor right here, times that second derivative, which was 1/2 d by dx squared of the propagator from x to x prime.
Right.
Yes.
So line n to get the ones to agree?
Yes. Do you want me to? Yeah, let's go through that again. That's just the statement that the term. So let's view the terms in this equation that are zeroth order in delta t. Okay. On the right-hand side, we have the propagator from x prime to x. And on the left-hand side, we have n times this integral here, times that one, times the propagator. So all I have done here is declared that n has to be the inverse of that integral in order to get the terms zeroth order in delta t to agree. And then the terms that are first order in delta t are these terms here. You can see that, lo and behold, all of the delta t's cancel. Let's move an IH bar onto the other side. IH bar d by dt of the propagator. Well, we have, coming from the Taylor expansion, we had that second derivative term. That's going to give you the kinetic term in the Schrodinger equation. So if I did everything correctly, God damn, I did everything correctly. Minus h bar squared over 2m d by dx squared of the propagator. And then from this potential term, multiply that by IH bar, and you get plus v times the propagator. And this, of course, is Schrodinger's equation. Okay. I told you to roll up your sleeves. It's not a trivial derivation. There's a reason, actually, why this was not understood until actually quite relatively late in the development of quantum mechanics. It's actually an interesting historical note. I've assigned you at various times readings from Dirac's book on the principles of quantum mechanics. If you read chapter 5 in his book, which I'll suggest is reading not this week but the following week, you'll actually see a mysterious footnote saying that, roughly speaking, the phase of the wave function is the action, as we have viewed here, and that the unitary time evolution operator can be viewed as a sum over all paths of this exponential factor. Okay. That footnote was ignored for 20 years. Nobody really thought about it. Nobody really thought about a precise version of that statement until Feynman wrote his PhD thesis where he decided that he really wanted to understand quantum mechanics. And he gave essentially the derivation that I've outlined here for you today. And I should emphasize that this really is a completely different way of thinking about quantum mechanics. And it's a way that in some ways is technically rather difficult to deal with. I mean, as you've seen, the formal definition of a path integral involves this discretization and this complicated sum and these funny normalization factors. And in fact, path integrals in general are quite difficult to compute. But this provides a very nice way of reorganizing your thinking about quantum mechanics. And so, as we'll see next class, this provides a variety of very interesting ways of understanding some of the most important and interesting and unusual effects in quantum mechanics, as well as providing just, I think, a conceptually beautiful framework for thinking about particle dynamics and the meaning of quantum mechanics. Okay. So let me stop here and see if there are any questions. Okay, we're going to continue next time with a more detailed discussion of this path integral formulation.